A mechanical punch slices through a plastic sheet, driving a clean break through the material's cross-section. This parallel action, where one part of the material slides against the other, is the physical basis of shearing. In materials testing, shear strength is defined as the maximum load a material can withstand to shear a specimen so that the moving portion completely clears the stationary portion. While compressive stress pushes material together and tensile stress pulls it apart, shear stress acts in parallel. It forces adjacent planes of a material to slide past one another in opposite directions. When a bolt holds two plates together, it is subjected to a sideways force, trying to slice it in half. Similarly, packaging films must resist the parallel pressure applied during high-speed punching or perforation. By isolating this specific sliding force, engineers can predict exactly when these materials will fail in real-world applications. To standardize this measurement, ASTM standard D732 specifies exact sample dimensions. The specimen must be either a 2-inch diameter disc or a 2-inch square plate, with a thickness falling strictly between 0.050 and 0.500 inches. Every sample requires a 7/16-inch hole drilled directly through its center. This opening accommodates a metal guide pin from the testing tool, ensuring the punch stays perfectly aligned with the sample during the test. Once prepped, the specimen is locked securely into a specialized punch-type shear tool, which sits inside a universal testing machine. The test begins by driving the punch downward at a constant specified rate. As the metal forces its way against the plastic, the machine's load cell continuously records the increasing resistance. The resistance builds until the material yields and separates. The highest point on the curve, the maximum force required to push the punch entirely through the plastic, is our critical data point. Recording the maximum force is only half the job. To evaluate the material's properties, we must convert that raw physical force into a standardized measurement of stress. We find that value using a straightforward formula. Shear strength is equal to the force required to shear the specimen divided by the area of the sheared edge. This is where students often make a critical mistake. When calculating an area that involves a circular punch, the instinct is to calculate the surface area of the top of the plug. That calculates the flat face, which didn't experience the shear. The force was applied along the vertical, cylindrical wall that was cut away from the main plate. That is the actual plane of failure. To find the correct area, imagine you can unroll that outer edge into a flat rectangle. The length of that rectangle is the circumference of the punch, and the height is the thickness of the specimen. Let's test this out. If your machine records a peak force of 1,500 pounds on a specimen that is 0.2 inches thick, using a punch with a circumference of 3.14 inches, hit pause and calculate the shear strength. Dividing 1,500 by the product of 0.2 and 3.14 gives you 2,388.5 pounds per square inch. Memorizing equations without context leads to errors. Consistently applying the correct formula requires translating the 3D mechanics of the test into 2D mathematics. The ASTM D732 method has one notable limitation. When testing extremely thin specimens, the material often lacks the rigidity to hold its shape. Instead of shearing cleanly, it bends and stretches deeply into the die hole before tearing. Because the machine is now working against the plastic's tensile stretch rather than a pure shear force, the resulting data point will be artificially high. It prevents a true shear-type failure from occurring. When specific shear testing isn't viable or data isn't provided by the material supplier, engineers rely on a safe rule of thumb. For design purposes, shear strength is generally assumed to be 1/2 of the material's tensile strength. Full mastery of this method involves meeting 4 specific criteria: adhering to the ASTM D732 standard, defining failure as the point the moving plug clears the stationary sheet, using a 2-inch specimen with a 7/16-inch center hole, and calculating stress against the cylindrical wall of the cut. Knowing these parameters and the physical reasons behind them gives you the tools to analyze shear data accurately, whether you are filling out an exam paper or validating a structural design.